Welcome to Pomodoro Joe for Wednesday, July 26th, 2023. Today we're looking at LeetCode problem 1870, minimum speed to arrive on time. This is a medium problem. You are given a floating point number hour, representing the amount of time you have to reach the office. To commute to the office, you must take n trains in sequential order. You are also given an integer array, dist, of length n, where dist index I describes the distance, in kilometers, of the ith train ride. Each train can only depart at an integer hour, so you may need to wait between each train ride. For example, if the first train ride takes 1.5 hours, you must wait an additional 0.5 hours before you can depart on the second train. Alright, return the minimum positive integer speed, in kilometers per hour, that all trains must travel for you to reach the office on time, or -1 if it is impossible to be on time. Tests are generated such that the answer will not exceed 10 to the 7th, and hour must have at most 2 digits after the decimal point. Alright, then we have some examples here. Oh boy, this is a tricky one. Well, a couple ways come to mind how to do this. So I think I'm kind of inspired by yesterday's problem where we did a binary search. And this one actually seems like it might be a good fit for a binary search algorithm. So in this case, we'll have some function that tells us whether or not a speed is an acceptable speed. So we just say, will this speed get us there on time? Then we can just search all the different speeds between 1 and some maximum speed to see which one gives us the best answer. And it looks like we are bounded here. So it does say the answer will not exceed 10 to the 7th. So we could use that as our max, 1 as our min, and just do a binary search for our answer. So let's do that. So we'll put 25 minutes on the Pomodoro timer and we will get started. All right, so the first thing I think I'll do, let's do a quick early out. I don't know if this is necessary, but it might help us out. So how many departure times do we get? So this is the departure count. And that's going to be, let's see, I guess it's going to be, so if we have 1 hour, we get 1 departure. If we have 2 hours, we get 2 departures. But what if we get 2.5 hours? We get 2 departures. Not including the first one. If we have 2.5 hours, we can leave it hour 0, that's 1 train, leave it hour 1, that's 2 trains, and leave it hour 2, that's 3 trains. So this is kind of ceiling of the hour. I think that's right. Okay, now we can do a quick check. If we don't have enough departures to fit all of our trains in, then we have to return -1. So if departure count is less than the length of our train, our dist array here, then we'll return -1. We don't have enough departure times for all of our trains. All right, this isn't really necessary. Well, it might not be necessary. We'll find out later. Okay, now for our binary search algorithm, we'll need a couple things. One, we'll need to know our min speed and our max speed. Then we'll have to go through and find our best speed. The other thing we'll need is some function that tells us whether or not a speed is a valid speed. So let's have some function here called isValidSpeed. And we'll take a speed. All right, I'm just gonna pass on this for now and we'll come back to it. All right, what's our slowest speed then? These are gonna be our bounds. So the slowest speed is 1. It has to be an integer. It does say somewhere here, a minimum positive integer speed. So the minimum positive integer that we can have is 1. And what's our fastest speed? Well, it says here it's gonna be 10 to the 7th. So that's 10 to the 7th. All right, now we can start our binary search. So for this one, we're going to essentially take our slow and fast speeds, find the midpoint between them. That's going to be our check speed, our mid speed. So once we find this midpoint, we'll actually check, is that a valid speed? If it is a valid speed, then we can lower our fast speed to that midpoint speed. So that's lowering our confining our search area to a smaller set of speeds. If it's not a valid speed, if the midpoint is not a valid speed, well, then we have to move our slowest speed up to that midpoint because we don't have enough time to get to our office at that speed. All right, so while the slow speed is less than the fast speed, we'll find some mid speed here. And that's just going to be, well, for this one we need to find, well, what's the delta in our speeds? So that's fast speed minus our slow speed. So this is the delta between the speeds. And we'll do an integer divide by 2 to give us our midpoint speed. So now this will give us just the midpoint in terms of our range, but we still need to add in the base speed. So that's going to be slow speed plus this delta. This is fairly typical of our binary search type problems. If you saw yesterday's video, this is very familiar to you. So check out yesterday's video if this doesn't make sense. All right, so now we just check. If this mid speed is a valid speed, then we can reduce our fast speed. If this is not a valid speed, we have to raise our slow speed up. So if is valid speed, all right, if this is a valid speed, then our fast speed can be dropped down to this midpoint. Otherwise, we'll have to increase our slow speed to this midpoint, and we'll do +1 because we already know this midpoint isn't going to be valid, so we have to go at least a little bit faster than this midpoint. So that's slow +1. All right, and now at the end, we will return our slow speed. All right, so this should give us our base here. Now we have to do this, is a valid speed. How do we figure this one out? Oh man. Well, we can basically go through, calculate essentially how long it's going to take each train to make its distance, to cover its required distance, add up all these times, and if that time at the end is less than this hour, then we're good. All right, so let's have travel time here. Maybe we'll call it total time. All right, so the total time will start at 0. Then for every distance in our dist array here, so this is how far the train has to travel. So this is the current time that it's going to take. We have to cover this distance in this amount of time in our speed. So let's see, this is basically saying we have to do 10 kilometers and we're going 10 kilometers an hour. That's going to take us 1 hour. If we have to go 20 kilometers and we're going 10 kilometers per hour, that's going to take us 2 hours. So this is how many hours it's going to take us. And let's see, I don't want to do an integer divide. This is a floating point divide. All right. Now the total time will just increase by this time. But there's a slight catch here. So in our very last train, we might have some fractional hour. We might not have a full hour on that very last train. All right, so for each of our normal trains, we actually have to raise this up to the closest hour because we basically might have to wait for the next train. So normally we will actually have to call ceiling on this time. So that will take some floating point and raise it to the next closest integer greater than this current time. So this will give us basically our integer times or our departure times. But that's only if this is not the last train. Oh, so I might need to keep track of whether or not this is the last train. So I can't just use distance here. Oh, that's too bad. All right, let's do this. We'll have to say for index in range length of our distance. All right, so the reason I'm doing this, previously I could just grab the distance, figure out the speed and the time. Unfortunately, I need to know if this is the last train. And in order to do that, I'm going to use this index to tell me whether or not this is the last train. All right, so this will be dist at index I. All right, and that's if this is not the last index. So actually, let's create a helper variable out here. That's max index. That's going to be the length of our dist minus 1. All right, so if I is not the last index or max index, otherwise instead of using the ceiling, we won't have to wait around. We have to get to the office. But that means that this time is basically a fractional time. Okay. And then finally down here, we've calculated the total travel time for all of our train rides. Is this going to be less than or equal to our current given amount of time? So we will return total time less than or equal to the time that we're given, hour. Okay, so this should tell us whether or not we have a valid speed. I hope. Hopefully I did this right. All right, so now we have our binary search. We're just going through checking all these midpoints to see if they're valid. If they are valid, we can always lower our speed to see if we can find a slower speed that's valid. Or we can raise our speed up if this speed isn't valid. All right, I think this should be good. One concern here, well, we'll just run this and see. I do have one concern that I'm not necessarily checking whether or not this slow in the end is a valid speed. Anyway, we'll try this. We'll see how it goes. Okay, so this works. Let's see if this will pass all the tests. And we pass. All right. So how do we do? We do okay, not great. 47% for runtime and 25% for memory. That's not too bad. Yeah, that's not too bad. All right, let's jump back here and see if there's something else we can do. One thing, I'm calculating this length over and over and over again. So one thing we could do is just have disk length. All right, and we can use that here. So this is a minor optimization. Basically, I don't want to have to call length function every time I do this. So that might save us a little bit of time. All right, what else can we do in here? We could actually, well, I don't think this is taking that much time. We could actually just count out the 7, so 10 to the 7th, 2, 3, 4, 5, 6, 7. So we could do that. That might save us a little bit. All right, let's see if this still works. All right, it still works. Let's see how this goes. All right, let's see. Did that save us anything? That made 0 difference. I guess we got a little bit faster. We went from 47% to 48%. Not much faster. All right. I don't really know if there's a ton we can do here. We could try to wrap this in to here instead of making a function call. I don't know if that's going to be that much faster. Well, shoot. We could try getting rid of this, I guess. I don't know if this is strictly necessary. It was sort of an optimization that might have helped us, but let's see if this is... Actually, we might need that. Yeah, because otherwise we don't have this return -1. Okay, well, I think I'm going to leave any optimizations up to you, but let's just check out how other people do this really quick. We got a little bit of time. Let's jump in here. We're pretty much solidly in the middle of the pack. Let's see how some of these faster algorithms go. All right, so this one does not have an internal function. Oh, it does. It has this check. Oh, so it's doing the same thing we're doing, but it's using NumPy. Oh, that's pretty smart. So NumPy is a library for doing math. A lot of number stuff, especially really good stuff with matrices and arrays. So see what they're doing here. They're taking this NumPy array, or they're taking this distance and making it into a NumPy style array, which means that they can just call distance divided by their speed, v, I guess that's for velocity. So they can just do their time calculation really fast on the entire array just by making this one call, whereas I have a for loop because I'm going through every single element in the array. The other thing they're doing, they're using NumPy ceiling, which is the same basically. Oh yeah, so this is basically the same, and they're using, they're doing a sum. That's pretty smart too. So I'm going through and adding up the times individually. They're just going to create their entire array and then sum it. That's pretty smart. All right. The rest of this looks about the same. They have one optimization here. If there's only one train, they just return this value. So that's probably a smart one to do. I should have thought of that one too. Anyway, I'm going to leave that up to you. You can check this out. Again, this is LeetCode problem something, 1870, and it's a fun one. So check it out. All right. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.